So chapter 12 po is the modeling vaccination. So next slide. Thank you. Yeah. So in this chapter, we're going to discuss about vaccination or immunization, and in order to simulate and see the results with the immunization, we're going to use the same scenario, yung freshman plague po last meet, and some of its function po na diniscuss doon. So next slide. Yan, so ito po yung mga functions na ginamit kanina or ginamit last meet, sorry. So si make system, stress simulation, and si update function. So ayan, so next slide. Ayan. So if you remember yung last meet, so diniscuss ni Francis yung about sa SIR or sa KM model no sa disease. So ngayon, i-implement natin dun sa program na yon yung immunization. So kung ano nga ba yung immunization? So immunization is a way that a person is protected against an infectious or lethal disease by vaccination. So yung process po ng vaccination, so like hindi na po sa atin bago 'yon kasi we're in a pandemic situation po, and it is going to it prevents the disease to spread further and help recover dun sa mga na-infected. Next slide. So ayan. So now we're gonna implement the immunization function dun po sa scenario last chapter. Ayan, next slide. So ito po yung gagamitin natin na function. So ayan, referring to the scenario from the freshman plague, ito po yung gagamitin natin na function. So ang pangalan po ng function natin is si at immunization. So makikita po dyan si system.init S. So ayun po si susceptible, and si system init R na si recovered. So ang ginagawa po ng function na ito ay i-move po yung given population po from susceptible to recovered. Kasi po 'di ba kapag po nabavaksinan ka, sa part na hindi mo na po kailangan ma-infect para po magpa-vaccine kasi ayaw mo na maranasan yung effect po nung plague or ng disease. So magpapa-vaccine ka na po to be resistant po sa population, and kumbaga yung resistance na po na yon mapapunta mo siya sa recovered part po ng fraction. So kumbaga hindi ka na po mag-undergo nung infection phase po nung sa disease, and diretso ka na po sa recovered part. So next slide. Ayan. So ito po yung so gagamitin na po natin yung scenario for the last chapter. So ito po yung given parameters po. So si time, contact in days or recovery time, then si contact rate and recovery rate per day. So sa left side po si system 1, ayan po yung scenario dun sa last chapter. So ayan po yung part na without immunization. Then since ngayon i-implement natin yung immunization, mag-add po tayo dun sa code ng add immunization part na tatawagin natin system 2, then point 1. So si point 1 po dyan, ayan po yung rate. So it can be interpreted as 10% or 0.1 decimal. So, kayo po bahala. So next slide. So after po nyan, meron po siya siyempre plotting ng data para po sa better understanding po nung simulation. So after po nung running ng code, ayan po yung lalabas na graph. So si blue dashed line, siya po yung no immunization na result, and si orange po si 10% immunization. So kung makikita niyo po dyan, mga siguro po may difference po na mga 0.1 or 0.2, in-estimate ko lang po na para difference po na make ng 10% immunization do sa population. Ayan. So para po makita natin na statistically yung outcome po ng graph, here comes the metrics. Next slide. Ayan. So ngayon po, i-discuss natin si metrics ng simulation. Next slide. Thank you. Ayan, so gaya nga sabi ko kanina, we're going to compute the statistical outcome of the previous model. So statistical outcome, so ito po yung naka-numbered for per percentage form po nung sa graph. Next slide. Ayan. So with that, ito po yung gagamitin natin na function for better visualization po. So si count total infected. So ang ginagawa po ng function na to is will compute the total number of sick students in the population. So ang ginagawa niya po is kukunin niya po yung susceptible before i-run yung simulation, then kukunin niya rin po yung susceptible nung after na na-run yung simulation, then i-minus po sila, then makukuha na po kung ilan po yung na-infect dun sa population natin. So ito po para mas makita natin, i-implement po natin siya sa example kanina. So next slide. So ayan. So i-implement natin siya sa kanina. So sa left side si system 1 or yung kaninang without immunization, then sa right side si system 2 na with immunization. So yung result po dun sa without immunization, so si 0.468, so or i-round up natin ng 0.47, and si with immunization ay 0.3065, rounded up as 0.31. So multiply natin by 100 para makuha natin yung percentage nila. So si without immunization ay 47%, tapos si with immunization ay 31%. So yung kanina sabi ko, diba doon sa graph, in-estimate ko na mga 0.1 or 0.2 yung difference niya. So now, by subtraction, malalaman natin na precisely 16% yung na bring down ng 10% kanina na immunization rate dun sa ating population. So dun sa example kanina, 0.1 or 10% rate lang. So paano kapag 20%, 30% or higher? So dito papasok si sweeping immunization. Next slide. Ayan. So next slide pa ulit. Ayan. So para sa different batches ng immunization rate, so we're gonna add, so itong part na to, we're gonna see the effects of sweeping the immunization rate in the said population. So next slide pa ulit. Sorry. Ayan. So ito yung code natin for sweeping the immunization rate. So ayan. So this function will map each immunization rate. So simula 0.1 hanggang 100%. So to the resulting fraction of the students infected. Next slide. Ayan. So yung function na yun, we can call natin siya by fraction underscore array. So equal to linspace from 0 to 1, 21 steps. So tapos infected sweep immunity fraction underscore array. Tapos syempre for plotting para sa visualization natin sa graph. So ayan. So sa x-axis na si fraction immunized, then si y-axis is the total fraction infected. So para sa result, ayan, next slide. Ayan. So ayan yung graph once na-run yung different immunization rate. So nakalagay dyan si 0%, 20%, 40%, 60%, 80%, and 100%. So ayan. For the analysis sa graph, para mas maintindihan natin lalo, so as you can see in the graph, as the immunization rises, yung immunization rate, the infection rate or yung mga na-infect ay bababa na bababa. So makikita mo pa lang doon sa 40% or doon sa 40% ng students, makikita mo na like mga less than 4% pa lang, 4% na lang yung naapektuhan ng disease. Kasi sa pagba-vaccine, hindi lang naman yung na-vaccinan yung mapoprotektahan. So yung mga nakapaligid din sa kanila. So yung tawag doon is si herd immunity. So You might have heard it since kasi nasa pandemic situation tayo. It is where the disease cannot spread further since the people around it is vaccinated, hence increasing the number of resistance, and therefore ma-isolate yung disease and hindi siya mag-spread further. So another analysis do sa graph. So kung makita nyo yung curve niya banda sa may 0.2 to 0.4. So may kumbaga may good and bad side yon. So good side kasi dahil nga herd immunity, hindi mo na kailangan i-vaccine the 100% of the population. So doon sa graph, like 40% to 60% pa lang stable na yung line niya na hindi na ganoon tataas yung infective fraction sa population. Pero negative side yon kasi dun sa kapag nagbago from 0.6 to 0.4 yung pag-change ng immunization rate, hindi siya ganoon kakita na hindi ganoon ka constant yung change niya dun sa pagtaas or pagbaba ng fractionally infected. Pero kapag dun sa 0.4 to 0.2, makikita mo yung curve doon na yung effect nung pagbaba ng immunization rate, tataas din yung fraction infected. So, with that, next slide. So, yun lang naman yung sa pag-i-implement ng immunization functions. So, for the summary for this chapter, so in general, models are used to predict and explain the design. And in this chapter, we use a SIR model to predict the effect of the immunization to explain the phenomena of herd immunity. And sa next chapter, my expertise is sweeping the parameters. And for the exercises, so hindi na kayo magpa-exercise kasi self-explanatory naman kasi yung pag-immunization. And for the next chapter, thank you.
For the sweeping parameter, next slide po. So, the contact rate beta is a measure that captures the likelihood of a person becoming infected with a disease based on their interactions with others. It takes into account both the frequency of interactions between individuals and the probability of infection during those interactions. The larger the population, which is the N, the larger the number of the susceptible, which is the Sn, who are at the risk of contacts with susceptibles and other people is represented by beta Sn, and the number of those contacts where the other person is infectious is represented by beta Sin. As the contact rate increases, the total number of infections is also expected to increase. To better understand this relationship, a range of values for beta can be created and analyzed. So next slide po. So the code here in sweeping beta is simulating the spread of an infectious disease in a population using a simple mathematical model known as the SIR model, the susceptible infected recovery. The SIR model describes the dynamics of the spread of a disease in a population by dividing the population into three groups: susceptible individuals who have not yet contracted the disease, infected individuals who have contracted the disease, and recovered individuals who have recovered from the disease. So as the beta increases, we expect that the total number of infections to increase. So the beta array variable is an array of 11 values from 0.1 to 1.1, which will be used as the contact rate in the simulation. The gamma variable represents the recovery rate. So for the sweep beta function, it takes the beta array and gamma as arguments and runs the simulation for each value of beta in the array and returns a sweep series with the total number of infected individuals for each value of beta. So, next slide po. So, the infected sweep variables stores the result of the sweep beta function. So before we plot the results, we will going to use the formatted string literal, also called an F string, to assemble a label that includes the value of gamma. Next slide po. And the infected sweep dot plot function plots these results, showing how the total number of infected individuals changes as the contact rate changes. So this figure is a representation of how the parameter beta, which is related to the contact rate, affects the outbreak of an infectious disease in a population. The x-axis represents the value of beta, and the y-axis represents the fraction of the population that becomes infected. So when the beta is small, the contact rate is low, and the outbreak does not spread widely. So as the beta increases, it reaches a threshold near 0.3 where the number of infected individuals increases rapidly. When beta exceeds 0.5, a large proportion of the population, more than 80%, becomes infected. The figure represents a parameter sweep, meaning that it shows how the outcome changes as the parameter is varied, not a time series. So next slide po. So for the sweeping gamma, the value of gamma determines the rate at which individuals recover from the disease, and thus it affects how long people are infectious. When gamma is low, individuals takes longer to recover, which means that they can transmit the disease to more people. So even if the contact rate or the beta is low, the disease can still spread rapidly. So for the code, this code creates an array called gamma array that contains 4 evenly spaced values between 0.1 and 0.7 using the linspace. Then it enters a for loop which takes each value in the gamma array one at a time, assigns it to the variable gamma, and runs the sweep beta function with the current value of gamma. So after running the function, the return value is assigned to infected sweep, and the label for the current value of gamma is created using a string formatting. So this process repeats for each value in the gamma array, and the resulting plots are decorated with X label contact rate beta and Y-axis label fraction infected. So in the end, the script plots the total number of infected individuals for each value of beta, with each line representing a different value of gamma. So when the recovery rate gamma is low, it means that people take longer to recover from the disease and are infectious for a longer period of time. In this case, even a low transmission rate or the beta can result in an outbreak or epidemic. On the other hand, when the recovery rate is high, the transmission rate or the beta needs to be higher in order for the disease to spread and cause an outbreak or epidemic. Next slide po. So for the using a sweep frame. Next slide po. So the sweep frame allows the user to easily visualize the result in different ways. Next slide po ulit. So kung mapapansin nyo po, itong sa using of sweep frame, same po siya dun sa sweeping gamma. So this time po, we're going to visualize this in a different way. So the function sweep parameters takes into 2 arrays of values for beta and gamma respectively. It creates a sweep frame to store the results, where each row corresponds to a value of beta and each column corresponds to a value of gamma. Inside the loop, the function runs with beta for each value of gamma and assigns the result as sweep series object as a new column in the sweep frame. So the values in the frame represent the functional population infected for each pair of beta and gamma. The resulting frame can then be plotted with each column corresponding to a different value of gamma and showing the impact of varying beta on the fraction of infected students. So next slide po. So this example demonstrates one use of sweep frame. We can run the analysis once and save the results and then generate different visualization. And also, the code also provides a contour plot function that can take the sweep frame and use matplotlib to generate a contour plot, which shows the parameters on the axis and contour lines where the value of the metric, the infection rate, is constant. Next slide po. And this time we're going to visualize the results of a dimensional sweep in a contour plot. So the contour frame part of the code is plotting a contour plot of the data contained in the frame variable. A contour plot is a way to visualize 3-dimensional data on a 2-dimensional surface by plotting contours or lines that represents different levels of the dimensional surface. The contours in this plot likely represent different levels of infection, the fraction infected in a population as indicated by the title of the plot. So the values of gamma are plotted on the x-axis corresponding to the columns of the sweep frame, while the values of beta are plotted on the y-axis. So next is which values are beta plotted on the y-axis corresponding to the rows of the sweep frame. Each line in the sweep frame follows a contour where the infection rate is constant. So as you move from the lower right to the upper left corner of the sweep frame, the infection rate increases. This is because as the contact rate or the gamma increases and the recovery rate or the beta decreases, the likelihood of infection also increases. In contrast, infection rates are lowest in the lower right corner of the sweep frame where the contact rate is low and the recovery rate is high. Overall, the use of sweep frame allows for efficient and flexible analysis of the simulation results, allowing the user to easily visualize the results in different ways and understand how different parameters affect the spread of the infection. So next slide po. So for the summary, this chapter is discussed the method for conducting a two-dimensional parameter sweep using a sweep frame to sort the results. The results are then plotted in three different ways. First is by plotting the total infections versus beta with one line for each value of gamma. Then by plotting the total infections versus gamma with one line for each value of beta. And finally, by making a contour plot with beta on the y-axis, gamma on the x-axis, and contour lines where the metric is constant. This visualization suggests that there is a relationship between the beta and gamma that determines the outcome of the model, which will be further explored in the next chapter through simulations and analysis. So next slide po. Next slide pa po. So, ma'am, hindi na rin po ako magpapa-exercise. So, sasabihin ko na lang po dito yung sa exercise po. So, this passage is discussing a method for estimating the parameters of an outbreak, specifically the infectious period and the time between contacts. The infectious period, represented by gamma, is known to be 2 days on average for the freshman plague. The fraction of the population that gets infected, represented by beta, is 40% during one particularly bad year. The method being proposed is to sweep beta with a fixed gamma and estimate beta based on the behavior of the outbreak. The passage uses the example of a crossings function that can be used to interpolate more precisely, although it is not specified what this function is or how it works. The final estimate of time between contacts is calculated as 1 per beta estimate. So next slide po. So the first line of the code sets the value of gamma, which represents the rate at which individuals recover from the infection to 1/2. This is based on the assumption that the infectious period for the freshman plague is known to be 2 days on average. The second line of code uses the sweep beta function to calculate the fraction of the population that gets infected for different values of beta, which represents the rate at which individuals come into contact with one another. The function takes in the beta array and the fixed gamma value as input and returns the infected sweep array. So the third line of code uses the crossings function to interpolate more precisely the value of beta that corresponds to an infection rate of 40%. This is based on the assumption that during one particularly bad year, 40% of the class is infected at some point. So, fourth line of code calculates the time between contacts, which is equal to 1 per beta. The result is stored in the variable time between contacts. So, next slide po. So, the output is 1.5987549. Next slide na po.
Chapter 14, Non-Dimensionalization. Slide. Exploring the result. Next slide.
Nawala. Nawala yung, natin, presentation. Ako lang hindi nakakakita. Teka lang, baka ako yung may problema. Meron ba kayong nakikita sa slide?
Meron po.
So ako ang wala. Teka. Ano kayang problema na sa akin? Okay. So wala akong nakikita. Wait lang. Teka. Babalik ako. Dali lang Okay. Join. Ayan. Okay. Meron na ulit. Sige. Shoshana. Go. Go na, go.
Go na po.
Oo, go na.
Sa previous chapter, we wrote a function called sweep parameters. Makikita natin siya sa chapter 13. Nag-run siya ng simulation for each pair of parameters. Tapos, i-return niya yung sweep frame na may kasama ng result. Now, i-run naman natin yung function na sweep parameters mula sa previous chapter. Tapos, ang gagamitin nating array of parameters ay itong sumusunod, yung nasa baba, which is yung beta array and gamma array. Next slide. Ito yung magiging itsura ng naunang parameters ng in table format. Yung mga row na parameters ay beta, tapos gamma naman yung column. Next slide. Para naman ma-print natin yung value ng sweep frame, gagamit natin itong code para makita yung result na nasa next slide. Next slide po. Yung first column ay yung beta, yung second column naman is gamma, tapos yung metric naman yung nasa third. Kung na-observe mo siya, pati yung table, yung value ng 0.1 beta and yung 0.2 gamma sa table at dito sa output ay same value ng nauna, which is 0.010756. Yung table is mostly for visual representation, tapos itong result naman is yung output ng pie chart. Next slide. Ito yung first example ng one for loop inside another for loop. Kapag nirun yung outer loop, it select gamma from the column and extract the corresponding column. Tapos, yung isa pang dahilan ay kapag nirun yung inner loop, pipili siya ng value of beta mula sa index column and select the corresponding element, which is ito yung fraction ng population na infected. Next slide. Ito yung next set of codes na gagamitin para gagamitin niya rin yung same loop sa nauna para ma-enumerate yung element ng sweep frame. Pero itong code, i-display niya yung plot point ng sweep frame. Next slide. Ito yung graph ng sweep frame. Yung x-coordinate ay ratio beta over gamma and metric or fraction of the population infected yung y-coordinate ng graph. Yung graph, isa siyang single curve. Ibig sabihin, ito yung pwede nating predict yung fraction of the population that will be infected sa single parameter, which is yung ratio beta over gamma. Next slide. Contact number. Sa chapter 11, yung number of new infection ay binibigay as beta SIN. Tapos yung number of recoveries naman ay gamma IN. I-divide sila para makuha yung beta S over gamma, which is number of new infection per recovery. Kapag yung bagong disease in-introduce sa susceptible population, yung S is approximately 1, beta over gamma naman yung number of people infected by sick person. Tinatawag din contact number or basic reproduction number yung ratio beta over gamma. Tapos yung contact number naman is denote siya R sub 0 sa mga SIR model, pero letter C yung gagamitin sa equation na nasa module. Itong step 1 ay yung differential equation mula sa chapter 11 na gagamitin natin para makuha yung C or contact number. Tapos, i-divide natin yung contact rate by infection rate para makuha yung dimensionless quantity ng C. So, i-divide natin yung I over T by S over T para makuha natin yung ratio of rate na nasa step 2. Tapos, itong step 3 naman yung simplification ng equation na nasa step 2. Tapos, yung gamma over beta S sa step 3, pinalitan siya ng 1 over CS. Also, dividing one differential equation by another is useful because it gives us relationship between IS and C na hindi dumedepende sa time. Next slide. Next is divide natin yung equation na nasa step 4 by DS both side. Tapos, ang magiging resulta niya is yung nasa step 5. Next, i-integrate natin yung both side ng equation sa step 5 para mag-result dito sa step 6. After natin makuha yung result sa step 6, kailangan natin siyang i-arrange yung equation kaya kinalabasan ay yung nasa step 7. Sa simula ng pandemic, kapag mababa yung fraction infected at halos lahat ay susceptible, gagamit ng approximation na 1 open parenthesis 0 close parenthesis equal to 0 and S open parenthesis 0 equal 1 para makompute natin yung Q. Tapos, ang lalabas ay S ay itong nasa step 6. Dahil pinalitan natin yung I and S. Also, dahil log 1 equal to 0, meron tayong Q is equal to 1. At the end of pandemic, mag-a-assume tayo na yung I infinite is equal to 0, tapos yung S infinite ay isang unknown quantity called S sub infinite. Kaya meron tayong equation na ganito sa step 9. Then, itong nasa step 10, ito yung hinahanap nating contact number mula sa equation na nasa step 9. Next slide. Analysis and simulation. Iko-compare natin yung analytic result sa result ng simulation. Para doon, gagamitin natin yung array of value, which is yung nasa unang picture. Tapos, itong sa C array, i-compute niya yung corresponding value ng C. Tapos, para makuha natin yung total infected, i-compute natin yung difference ng S0 and yung S infinite. Tapos, itong frac infected, yung ilalagay sa series para makuha yon, which is yung nasa second picture tsaka yung nasa third picture. Tapos, sa Modsy library, meron din na make series na pwede natin gamitin para ilagay yung C array at frac infected sa panda series. Ito yung frac infected series, which is yung nasa huling picture. Next slide. Para naman makita natin yung graph na ipa-plot, kailangan natin gumamit ng matplotlib sa pie chart. Ito naman yung plot swept frame. Next slide. Ito yung graph na makikita natin after natin i-run yung program. Kapag yung contact number lumagpas ng 1, nag-a-agree yung analysis at simulation. Kapag naman less than 1, hindi nila ginagawa yung sumusunod. Hindi ini-indicate ng analysis na walang infection. Tapos sa simulation naman, hindi ini-indicate yung kung may small number of infection ba. Yung reason ng pagkakaiba nila ay dahil yung simulation, dinedivide niya yung time sa isang discrete series of days, tapos yung analysis naman, yung time ay tinitreat niya sa continuous quantity. Kaya kapag malaki yung contact number, nag-a-agree yung dalawang model, kapag maliit naman, naghihiwalay yung dalawang model. Next slide. Estimating contact number, we can estimate the fraction of the population that will be infected with just a few arithmetic operation based on the previous slide. We can also read the figure in another way. First, we know what fraction of the population was affected by the previous outbreak. We can estimate the contact number. Second, if we know one of the parameters like gamma, we can use contact number to estimate the other parameters like beta. Next slide. Summary, we use simulation to explore the relationship between beta, gamma, and fraction infected and use analysis to explain the relationship. Hindi na po ako magpapa-exercise, ma'am.
Sige.
Okay na po. Tapos na po.
Okay. Right. Okay. So, therefore, we move on to the next group. Ayan. So, ay, ibang ano pala to. Sorry. 2-2 Okay. So, moving on tayo sa group 3. Group 3 na ba? Chapter 15?
Yes.
Okay.
Opo, ma'am. Pero po yung isa po naming member, di daw po makapasok. Siya po yung first reporter namin.
Pati siya
Wait lang
makapasok. Hindi siya
Kanina pa po kami nagkakaroon ng problem sa Meet po.
talaga? Wait
Opo.
lang. Sino yun?
Si Marceliana po.
Marceliano. Tingnan natin sa listahan. Marcy. Hindi siya makapasok? Bakit kaya hindi siya makapasok? Siya yung una. Sige, gawin natin siyang special. Para ano. Okay? Gagawa lang ako ng isang ng meet for this purpose. Then balik tayo, ha? Guwawa naman eh. Dali. Siguro naman pagka ito yung ginamit natin, okay na siya. Or internet niya yung problema. Copy link. Okay. So, guys, hindi tayo aalis dito. Mag-ano lang tayo ng another temporary lang. Ayan. Google Meet. Okay. Para lang dito kay and then afterwards, balik tayo, no? Okay. Right. Gamitin natin yan. Tapos, ilagay natin sa GC kay Marceliano. Okay. Anong name niya doon? Sana yun? Sana nagsarado. At ito. Marceliana. Si Nicole? Nicole ba yun? Ayan. Okay. So,
Yes, ma'am. Siya lang po yung magjo-join sa link. Tama
Hindi.
po.
Hindi. Yung buong grupo lang.
Kami pong buong group.
Yung buong grupo tapos ako. Ayan. Tapos, dun sa mga gustong pumasok para makinig, sige, pasukin nyo. Kasi to additional na Ayan. So, okay. Kahit ako lang dito, pwedeng pagkatapos ng reporting ni balik tayo, no? Ayan, admit. Asa na si Marceliano? Admit. Okay, and then sandali lang ito, class, ha? Sandali lang dahil babalik din tayo kay para lang dito sa reporting ng group na to. Andito na siya.
Wait lang po. Check ko lang po.
Check nyo nga. In here na. Sino yung in here na yan? Nandun na siya sa
Ay ma'am, hindi po. Nandito na po siya sa Meet po. Naayos
okay,
na po yun.
Sige.
Hello?
Okay, start na siya.
Sige po, wait lang po. Share ko lang po muna yung
Bakit
screen.
kasi hindi ka makapasok, Nicole? Ano kaya nangyayari sa Meet mo? Sa Teams mo?
Kita na po ba, ma'am?
Yes.
Okay po.
Ayan na.
So, ayan po. So,
Close na natin
good
to.
afternoon,
Guys,
everyone.
pa-close ko na tong Google Meet ha. Nandun na siya eh.
Sige po. Thank you po.
Alright. Okay, go.
Okay po. So, good afternoon po, everyone. So, our report will cover two topics. First po is cooling coffee. So, yung first half po ng report namin will involve something about coffee, and the other one concerns about medicine po. So, let's start po sa first report namin. So, cooling coffee. Reporter, please.
Hello po. Rinig po ako.
Yes.
Sorry po if ganito yung boses ko. I'm really not feeling well. So if ever may hindi po kayo marinig, paulit nyo na lang po ulit. Ayan. So the coffee cooling problem was discussed by Gerald Walker and the amateur scientist in November 1977. And since then, it has become a standard example of modeling and simulation. The problem is, suppose I stop on the way to work to pick up a cup of coffee and a small container of milk, assuming that I want the coffee to be as hot as possible when I arrive. And when I arrive at work, should I add the milk at the coffee shop, wait until I get to work, or add the milk at some point in between? Next slide. To help answer this question, gumawa muna ng trial run with the milk and coffee in separate containers, and the following are the measurements and results. When served, the temperature of the coffee is 90 degrees Celsius, the volume is 300 ml. Second is the milk is at an initial temperature of 5 degrees Celsius, the volume is 50 ml. Then the third is the environment temperature, which is yung environment dun sa car, is 22 degrees Celsius. The coffee is served in a well-insulated cup. Then after 30 minutes when it arrived to work, the temperature of the coffee had fallen to 70 degrees Celsius. The milk container is not as well insulated. Then after 15 minutes, it warms up to 20 degrees Celsius. To understand how coffee cools and milk warms, we need a model of temperature and heat. Quick review lang, yung temperature is yung property ng object or system. It is measured in degrees Celsius. Temperature yung nagko-quantify like how hot or how cold the object is, which is related to the average velocity of the particles that make it hot. When particles in a hot object contact particles in a cold object, the hot object gets cooler and the cold object gets warmer because the energy is being transferred from one to the other. Yung transferred energy na yon is what we call heat, which is measured in joules. Next slide. Heat is related to temperature by this equation. Kaya nakita niyo sa slide. Yung Q is equal to C times change in temperature, where Q is the amount of heat transferred to an object, and then yung triangle T is yung change in temperature, and yung C is yung object thermal mass, which is a property of the object that determines how much energy it takes to heat or cool it. Next slide. Then for objects made primarily from one material, thermal mass can be computed like this. Yung C is equal to M times C subscript P, where M is the mass of the object and C subscript P is the specific heat capacity of the material, which is the amount of thermal gas per gram. We can use these equations to estimate the thermal mass of a cup of coffee. The specific heat capacity of coffee is probably close to that of water, which is 4.2 joules per gram per degree Celsius. Assuming that the density of coffee is close to that of water, which is 1 gram per ml, then the mass of 300 ml of coffee is 300 grams, and the thermal mass is 1260. Next slide. So when a cup of coffee cools from 90 to 70, the change in temperature is 20 degrees Celsius, which means that 25,200 joules of heat energy was transferred from the cup and the coffee to the surrounding environment. Next slide. In a situation like the coffee cooling problem, there are like 3 ways heat transfers from one object to another. The first is conduction. It is when objects at different temperatures come into contact. The faster moving particles of the higher temperature object transfer kinetic energy to the slower moving particles of the lower temperature object. Then next is convection. It is when particles in a gas or liquid flow from place to place. They carry heat energy with them. The fluid flows can be caused by external action like steering or by internal differences in temperature. Then the last one is radiation, wherein as the particles in an object move due to the thermal energy, they emit electromagnetic radiation. The energy carried by this radiation depends on the object's temperature and surface properties. Convection can be a complex topic since it often depends on details of fluid flow in 3 dimensions. But for this problem, we will be able to get away with a simple model called Newton's law of cooling. Next slide. And Newton's law of cooling
Naka-base sa
asserts
temperature. Alright, sige.
Newton's law of cooling asserts that the temperature rate of wait lang po, inom lang ako tubig.
Ako din, inom din ako ng tubig. Ay.
Ayan, okay na po. Newton's law of cooling asserts that the temperature rate of change for an object is proportional to the difference in temperature between the object and the surrounding environment. Or if ilalagay natin sa equation, ayan, yan yung nakalagay sa screen. Wherein yung small t is yung time, then yung capital T is yung temperature ng object. Then yung T subscript, E and V is the temperature of the environment, and R is a constant that characterizes how quickly heat is transferred between the object and the environment. With that, we need to decide whether to treat the coffee and the cup as separate objects or a single object. If the cup is made of paper, then it has less mass than the coffee, and the specific heat capacity of paper is lower too. And in that case, it would be reasonable to treat the cup and coffee as a single object. However, for a cup with substantial thermal mass like yung mga ceramic mug, we might consider a model that computes the temperature of coffee and cup separately. Next slide. And moving on to the implementing Newtonian cooling, gawa tayo ng function na nagtitake ng parameters ng system, which is yung initial temperature, volume, R, and yung time end. Then gagawa rin tayo ng system object. In addition pala dun sa parameters, yung make system na function, mag-set din tayo ng temperature of the environment, initial time step, yung time step, tapos gagamitin natin siya para ma-simulate yung cooling process. Then, gawa rin tayo ng system object na nagre-represent ng coffee. Ayan yung nasa pinakababa. Yung values ng initial temperature, volume, and nung end time, galing siya dun sa statement of the problem kanina, yung trial run, if naalala nyo. In which the initial value ng coffee is 90 degrees Celsius, tas yung volume is 300 ml, and it took 30 minutes to arrive at work. Then yung R is arbitrary muna sa ngayon. Next slide. Newton's law is a differential equation, but over a short period of time, we can approximate it with a difference equation, which is, ayan, change of temperature is equal to negative R times temperature minus environment temperature times the time step. The following function takes the current time, the current temperature, and the system object, and i-compute niya yung change in temperature during the time step. Ayan, insert lang natin yung equation dun sa IDE sa Python. Then, test natin siya with the initial temperature ng coffee. With a time step equal to 1 minute, the temperature drops by about 0.7 degrees Celsius, at least for this value of R. Next slide. And ito yung version ng run simulation that simulates a series of time steps from initial time to end time. Gumamit tayo ng linear range, to make an array of values from initial time to end time with time step. It takes a start value and an end value and return an array of equally spaced values and a step size that indicates the interval between values. Then, when we make the time series, we use the keyword argument index to indicate that the index of the time series is the array of timestamps. Gumamit rin tayo ng iloc in which the label in brackets is always an integer starting at 0. So we can always get the first element with iloc index 0 and the last element with iloc index -1. In this version of run simulation, the loop variable is an integer that goes from 0 to n-1. So the first time through the loop, I is 0 and the value we add to the time series has index 1. The last time through the loop, I is n-2 and the value we add has index n-1. So next slide. Run natin yung simulation. Then the result is a time series with 1 row per time step. Tignan natin yung first rows. Ayun yung nasa left. Gamit lang tayo ng results.head para makita yung first few rows. And then yung results.tail naman, gamitin natin para dun sa last few rows. So when the initial time is equal to 0, end time equals 30, and time step equals 1, the timestamps go from 0 to 30. Ayun yung range na. So next slide. Then ayan naman yung magiging itsura pag pinlat natin siya. So in conclusion, the temperature of the coffee after 30 minutes is 72.3 degrees Celsius. So para mahanap naman natin yung value ng R where the final temperature is precisely 70 degrees Celsius, pwede tayo mag-trial and error actually. Pero mas efficient if gagamit tayo ng root finding algorithm, which is i-discuss nung next report.
Hello po, narinig ko ba ako?
Yes.
Okay po. So, we know from earlier that we can simulate and measure how the coffee will turn cold as we travel to work using Newton's law of cooling, where it was stated that the temperature rate of change for an object is proportional to the difference in temperature between the object and the surrounding environment. From the formula of Newton's law of cooling, we know that we need to find R, which represents a constant that characterizes how quickly heat is transferred between the object and the environment. In finding roots, we'll learn how to use the Modsy library function called root scalar to find the roots of a nonlinear equation. So, our root is a value of x such that when substituted to a function, will make the function equal to 0. So in the example function, we will know that the roots are 1, 2, and 3 because when you substitute 1 to the first part of the equation, it will become 0, and 0 when multiplied to any number will become 0 as well. To show how root scalar works, we'll be using the previous polynomial and we'll define it in a function. Then we will use root scalar to determine the roots of that function. So, root scalar takes two parameters or arguments. The first is the function whose roots we want to get, and then the second argument is an interval that contains or brackets a root. Basically, we're giving the function a range of numbers where we think a root can be found. So when we run root scalar, it will output several variables such as converge, which will return true if the search converge on a root, and the root variable, which is of course the root that was found. Next slide, please. Yeah, so if the interval or the range that we give to the function does not contain a root, we'll get a value error and the message like f of a and f of b must have different signs. So yung nasa slide, pinakita lang yung mangyayari if gumamit tayo ng ibang bracket for the roots. Next slide, please. So going back to our problem, to use the root scalar function in finding r, we must first estimate r so that we can get the interval that we can use for the root scalar function. So what we're going to do is to define a function that will take a system and r as a parameter and returns the difference between the final temperature and the goal. This way, we will know how near or far we are to the value of r that we are looking for. So we define here a function called error_func. Basically, what this function do is take r and subtract it to our goal temperature, which is 70 degrees. So we are left with the error value. If the value of r is right, our error should be 0. We'll be using our initial guess for r, which is 0.01, and run it through our function. The result is an error of 2.3 degrees Celsius, which means that 0.01 is too high since it's greater than 0. We'll then do another guess for the value of r, and since we know that 0.01 is too high, our guess should be less than 0.01. In this example, we use 0.02. Running it through our function, we get negative 11 degrees Celsius, which means that it was too low. But that also means that the correct value of R should be in between 0.01 and 0.02. Since we already have the interval, we can use the root scalar function now. Next slide. So, using all the data that we collected and running it through the root scalar function, we'll get 0.0115. Next. And when we substitute it the value of R to 0.0115 in the earlier change function, we'll get an estimated 70 degrees Celsius in our temperature, which means that we finally now have the data that we need to accurately simulate how the coffee cools as we travel to our work. Next. Next slide. So, mixing liquids. Now we already found out how the coffee cools, and we can just do the same process to find out how the milk warms, but the question remained unanswered. Is it better to mix the coffee and the milk at the beginning, at the end, or somewhere in the middle when we go to work? To find out, we will now be mixing these two liquids. So in mixing two liquids, the temperature of the mixture depends on the temperature of the ingredients, as well as their volumes, densities, and specific heat capacities. So assuming that there would be no other chemical reaction to produce or consume heat when we mix, the total thermal energy of the liquid should still be the same before and after mixing. That means that their thermal energy is conserved. So in the first formula, we have the thermal mass of the first liquid multiplied to the final temperature of the mixture, that's the T, and then minus the temperature of the first liquid, that's the T sub 1. Then adding that to the thermal mass of the second liquid, which is the C sub 2, multiplied to the final temperature of the mixture minus the temperature of the second liquid equals to 0. We equate our whole formula to 0 because, as stated, the total thermal energy of the system is conserved before and after mixing, which means that no energy is passed before and after we mix. So now that we have this formula, we can rearrange it to find the formula for the final temperature of the mixture. Yun yung andito sa left side. Once we do that, we'll get this formula where T represents the final temperature of the mixture, and then we have C sub 1 times temperature of the first liquid plus C sub 2 times temperature of the second liquid over C sub 1 plus C sub 2. So in this formula, we have the thermal mass, which is represented by the variable C. And the formula for thermal mass is density times volume multiplied by specific heat capacity. Yun yung formula dito sa right, yung C is equals to. And then in here, P stands for density, V for volume, and C sub P for specific heat capacity. So for this question, we are going to assume that the liquids have the same density and heat capacity. Because of that, we're going to cancel them out. Next slide, please. So nung kinancel natin yung P tsaka yung C sub P sa earlier formula, ang natira is yung volume. So we're going to substitute that for C in our current formula. Thus, we should have the formula for the final temperature, which is yung nakikita nyo sa screen yan. So now we are going to simulate the mixing process. So we're going to create a function that takes two system objects, one for coffee and one for milk, and creates a new system to represent the mixture. Next, please. So in this function, the first two lines extract the values of the volume and temperature from our system objects, yung coffee and milk. Then the next lines are about the computation for volume and temperature of the mixture. The function then creates a new system and stores the result of the above computation in there. Finally, with all those stuff done, we have everything we need to solve the problem. Next slide, please. So to answer the question if it is better to mix the drink first before going to work or mix it when you arrive at work, let's simulate some data. First, we'll create objects to represent the coffee and milk. For our coffee, we have the rate of temperature set to 0.0115, which is the one we computed earlier. Then we'll create a system that takes the following parameters. Initial temperature, which is 90 degrees Celsius. The volume, which is 300 ml. The rate of change in temperature of the coffee, which is the R. And then the temperature of the coffee when we arrive at work, which is 30 degrees Celsius. For the milk, we're gonna do the same thing. So we have 0.133 for rate of temperature change, initial temperature, which is 5 degrees Celsius, volume, which is 50 ml, rate of temperature change, and the temperature of the milk when we arrive at work, which is 15 degrees Celsius. Next. So for our first simulation, we're going to mix them first before going to work. So we just need to pass them as parameters to our mix function, then simulate it. That should give us the answer of 61.5 degrees Celsius. To compare, we're going to run our second simulation where we mix the liquid when we arrive at work. So the first thing that we're going to do is simulate and run the system for coffee and milk so that when we use our mix function, it will use the end temperature instead of the initial one. That should give us the answer of 62.9 degrees Celsius, which means that it is better to add the milk when we arrive at work, which made sense because when you add cold milk to a hot coffee, it will definitely cool a lot faster as opposed to adding lukewarm milk to a slightly cooled coffee. But we still need to find out if it's better to mix them at one point during our trip to work, so we're going to head to our next reporter.
Hello, narinig po?
Yes.
So, next naman is yung optimal timing. Adding the milk after 30 minutes is better than adding it immediately, but maybe there's something in between that's even better. To find out, we'll use the following function which takes the time to add the milk, t_add as a parameter. Ito naman yung function named run and mix na gagamitin natin to simulate both systems for the given time, t_add. Then, it mixes them and simulated the mixture for the remaining time na mailalagay natin sa formula na t_total minus t_add. Tapos, when t_add is negative, we can add the milk immediately. If t_add naman is 30, we can add it sa end na. And now, we can sweep the range of the values in between. Next slide po. Ayan yung sweep series na inilagay natin sa variable na sweep. Then, we plot it using the sweep series na ginawa natin. Tapos, after nyan, lalabas yung graph and nandun yung results. Next slide po. So, ayan na yung slide, ay yung graph. Pero, hindi ito time series and rather, isa siyang parameter sweep. Lastly, yung final temperature can be maximized when t_add is equals to 30. So, adding the milk at the end is optimal. Next slide po. So, next slide is the analytic solution. Where simulating Newton's law of cooling is not really necessary because we can solve the differential equation analytically. If the derivative of capital T divided by the derivative of small letter t is equals to negative r times t minus t sub n, yung general solution niya will be t times t equals cx times negative rt plus t sub n. And yung particular solution where t times 0 is equals to t sub init is t sub n plus negative t sub n plus t sub init x times negative rt. Next slide po. Now, pwede na natin magamit yung observed data to estimate the parameter r. If we observe that the temperature at t sub end is t sub final, we can now plug these values sa ating particular solution and solve for r. The result will be yung nakikita nyo sa screen, which is r is equals to 1 divided by t sub end log t sub init minus t sub end divided by t sub final minus t sub end. Next slide po. Then the following function takes a system object and computes r. We can use this function to compute r for the coffee with the given parameters of the problem. Tapos we will get the value of 0.01161022314227386. Itong value na to is close dun sa value ni r na na-compute natin last chapter, which is 0.115. Pero hindi siya exactly nakakapareho nun. The reason for this is because the simulations use discrete time steps and the analysis uses continuous time. Nevertheless, the results of the analysis are consistent with the simulation. To check this, we'll use the following function which takes a system object and uses the analytic result to compute a time series. Next slide po. Makikita natin sa first line is nag-unpack siya ng mga system variables. Then the next two lines computes the variable t_array, which is a numpy array of timestamps, and t_array with a capital T, which is siya naman yung array of the corresponding temperatures. The last two lines store the final temperature in the system object and use make_series to return the results in a panda series. Ngayon naman, if i-run natin siya, we'll get a temperature of 70 degrees Celsius, which is yung final temperature natin. Next slide. As what we can observe, identical na yung results na nakuha natin with a small difference due to rounding. So the first reason we simulated this is for validation. Since we solved the same problem in two different ways, we can be more confident that the answer is correct. The second reason is flexibility. Since meron na tayong working simulation, mas mapapadali na yung pagdagdag ng features. For example, yung temperature ng environment that might change over time, or we could simulate the coffee and container as two objects. If the coffee and milk are next to each other, we could include the heat flow between them. A model na may gantong features would be difficult or impossible to solve analytically. So, for the summary, in this chapter, we finished the coffee cooling problem from the previous chapter and nalaman natin mas okay na idagdag yung milk at the end. At least for this problem. Then, we'll have this exercise na may onting changes lang para makakuha tayo ng panibagong sagot. And, please answer exercise 1 for 10 minutes and magtatawag po kami ng 2 tao after that.
Alright. Exercise 1. Ano nga chapter ito?
16 po.
Chapter 16. Okay, buksan natin
Opo.
yung ating chapter 16 dun sa ating zip file ng Modsy. Ayan, so naandun siya. Okay, 10 minutes and we'll be back by 4:45. Pwede? Okay na yon?
Yes po, ma'am.
Okay. So, balik tayo ng 4:45. Gawin natin yung exercise. Share nyo lang dyan, ha? Huwag nyo alisin. Ayan. Tama na yan.
traffic on the highway and off-road. And it has those fantastic off-road. By far the best scooter I've been on for off-road. The 80 was 750. Look, I like that thing. It's big and heavy, and I don't like it off-road. It's difficult to find through traffic. It's just it's still fun once you're in. The 80 is 350 overall. The safest one is taking it off-road. It's on the traction control, full traction control, half traction control. Of course, off-road, very optional is more fun. But having that traction control on, you will not spin that back tire. I tried on super loose gravel, sand, and you don't have to spin that tire. Perfect for gravel roads, bad road conditions, potholes, mud. Right now, this is only offered in Thailand and Europe cars and all kinds of United States. If this makes it over to the US, I have no doubt it's going to sell fantastic. Right now, I have a Yamaha S-Track 330 in the US. If that's the speed, that's the roads over there, this would be perfect. One thing I need to mention, the headlights on this are fantastic. I'm making this point to see how great these are because my other favorite scooter, the Yamaha X-Max, headlights are terrible. I learned so many things about the Yamaha X-Max 300. The headlights are one of the worst things. It's like the number one thing I really don't like about that scooter. The headlights on this is awesome. Windscreen, just like 150 just right here. What I like about this, unlike those other scooters, especially the 4350, the screen's so big and the way it reflects the wind and all the way up, it kind of sucks your body on. So when you're maximum speed, it's kind of weird. All your clothes and everything's forward, where of course you don't get it from this one. It does like that. I think this is perfect, especially in Thailand with all these days. Gears are fantastic. They're in the perfect positions. One thing I noticed, of course, just like of course with reflecting gears, more instant vibration, and you also have your gears, especially in idle compared to the Yamaha X-Max 300. It's not an annoying vibration. It's really uncontrollable. In fact, if you ever rode the X-Max 300, I keep comparing it to the Yamaha X-Max 300 because, in my opinion, that's the next best one in this class. See, I've done all these big screens, very comfortable. I do like how the seat is tapered. It does let me get a little more airflow from here to the crotch. The Yamaha X-Max is bad. So you can use, in my opinion, is terrible about airflow. It's small for me. That's my experience. And of course, it's like the other scooter, you get that. Back there. Probably the best of the scooter. Maybe the best of the scooter right now. You're getting this is better than Yamaha. I'd say the top is very sensitive. It's hard. You feel confident using Yamaha. And a lot has to do with the life of the car. Have a lot of like the suspension going from the next best one was ride, a fun ride, with more history. Everything Yamaha 300 does, I love about it, is because the tires and rubbers are tires that give great traction on the dirt and gravel. This is sort of, I'm taking my Yamaha
Okay. 2 more minutes.
that's a big deal for me, especially riding in Thailand. And being older, I want something like going to a shop and being able to cruise around and fast. You have to be like very fast. You come around the corner, you get up the road, and you have to bump into the road, go to the corner. It doesn't smell the suspension. That's so big. I do like real safety. Of course, having places like this one right here, like I said, and all these quick ride. Let's go do a top speed test. I rode over to Chongqing City and back. It was 2 hours sitting on the seat. It was comfortable. All the controls are very intuitive. No reading necessary. Now my X-Max for sure. The seat's a little bit more comfortable. It's a little softer. Forza 350 is very comfortable.
Hello, may nakapagsagot na po ba?
Okay, pwede mo silang tawagin at random kasi oras na naman.
Sige po. Yung first presenter na po si Daniel.
Hello. Naririnig ba ako?
Yes.
Oo.
Ito yung nakuha ko. Wait, share screen ko lang po. Here. Nakita na po.
Aha.
Ito, ang gamit ko na lang din po ay yung sa notebook. So, nilagay ko na lang din po dito sa boxes yung solutions. Then, sabi po dun sa exercise 1 is parang itetest po yung consistency po nung sa result po nung simulations. Confirm that the results are consistent with the simulation. So, dito po, ang ginamit dito po nung value po nung milk2 is equals to make system. And value po nung T initial is 5 po and volume is 50. And R is equals to 0 po muna para para po dun sa initial nga po na test. Then, T end po ay is equals to 15. Then, yung milk 2 that T final po, ang value niya po is 20. Then, R milk is equals to compute R, yun nga po, yung compute R system. And milk 2, using yung milk 2 po. So, ang naging value po ng R milk 2 is yung 0.14267. Iba po siya dun sa kanina kasi iba din po yung ginamit na values nga po niya. Then, ito po yung, para naman po makuha yung both sides ng results at results 2. Ito po yung para sa result. Then, milk 2 is equals to make system. T initial is equals to 5. Then ang volume is 50 para po mapag-compare dito sa huli. Then, R is equals to R milk 2. Yung result naman po ng R milk 2 yung ginamit para dun sa R. Then, T end dyan po is 15. Then, results 2 is equals to run analysis milk 2. So, yung ginamit po sa taas. Then, ang ginawa niya lang po is yung sa milk 2. Yung ginamit ko lang po yung sa milk 2. Then, milk 2, T final, ang naging results niya po yung sa 20. So, katulad po nung lumabas dito 20. Then, milk is equals to make system, T initial, ang value po is 5, then volume is 50, then R is 0.13296, and ang value po ng T end is 15. Then results po, para po makuha yung results, run simulation, milk and change function. Then dito naman po sa parang po makuha kung yun nga po, in-import po yung sa all close, then all close results, yung results to and then itong result. Then ang naging ano bang tawag dito? Print niya po is true. So na-confirm niya po yung na-consistent po yung ayun po, yung result. Yun po.
Okay. That's good. Alright. Thank you, Daniel. Sige.
Okay na po yung tama naman po yung sagot niya. Next reporter na lang po.
Okay, next reporter. Pharmacokinetics.
Rinig na po ba ako?
Yes.
Okay po. So for our next reporting, So, we will talk about pharmacokinetics. So, ano nga ba yung pharmacokinetics? So, pharmacokinetics is the study of how drugs and other substances move around our body. Para nagre-react yung katawan natin sa different na gamot and para na-eliminate yung mga yon sa katawan natin. So, in this reporting, we will have focus dun sa interaction ng glucose and insulin within our body. So, ano muna yung glucose and insulin? So, glucose is a form of sugar that circulates in the blood of animals. Kasama na rin tayo doon. So, it's a form of fuel para sa body natin. Then, yung insulin, it is produced by the pancreas to regulate or reduce blood sugar or yung glucose. Now, yung process ng pag-release ng pancreas sa katawan natin is part of homeostasis, which is any self-regulating process by which an organism tends to maintain stability. So, hindi lang yung pag-release ng insulin yung part ng homeostasis, meron pang iba. But in our report, magpo-focus tayo sa homeostasis. Now, if the pancreas does not function well or yung mga cells na dapat nagre-react sa insulin is naging sensitive, nagkakaroon ng spike sa sugar level natin. So, that condition is called hyperglycemia. So, this happens when your body has too little or can't use insulin properly. Now, yung severe cases of hyperglycemia is a common symptom for diabetes mellitus, which is a group of diseases that affects how the body uses blood. Now, in testing glucose and insulin in our body, meron tayong tinatawag na frequently sampled intravenous glucose tolerance test or FSIGT. In this test, mag-i-inject tayo ng glucose sa bloodstream ng isang pasyente. So, dapat yung pasyente is a fasting subject. So, hindi pa dapat nakakakain. Then, yung blood samples are collected in intervals of 2 to 10 minutes for 3 hours. After nun, i-analyze yung measurement ng concentration sa glucose and insulin. So, dito napapasok yung glucose minimal model. So, the minimal model was proposed by Bergman, Eder, Bowden, and Cobelli. So, meron 2 parts yung minimal model nila. One is glucose model and the other one is insulin. But in our case, we will be talking about the glucose model. So, marami nang naging version, marami nang development sa minimal model na ginawa nila. So, pero there's something na kailangan nandoon lagi sa mga model. Sinabi nila na such a model must be simple enough to account totally for measured glucose given the insulin input, yet it must be possible to use mathematical techniques. Then, sinabi rin nila na merong features na important para sa minimal model. First is, pag in-inject yung glucose and na-elevate na siya, nagre-return siya sa basal level because of 2 things. First is, the glucose has the ability to normalize itself, to normalize its own concentration. Then, yung isa naman is yung catalytic effect ng insulin na i-allow yung glucose na mag-self-normalize. The other feature is, medyo mabagal daw yung effect ng insulin to net glucose disappearance. Because yung insulin daw kailangan mag-move from plasma to a remote compartment, which is later on na na-discover nila, which is the interstitial fluid, to exert its action on glucose disposal. Now na na-discuss ko na yung glucose and insulin and their interaction, mag-move on na tayo sa mismong formula na gagamitin natin for this simulation. Now, we have 2 differential equations. So this is the first one. It is read as the rate of change in glucose is equal to the negative k sub 1 quantity, the concentration of blood glucose as a function of time, minus the basal concentration of blood glucose quantity minus the concentration of insulin in the tissue fluid as a function of time, times the concentration of blood glucose as a function of time. Ay ma'am, wait lang po. May tumatawag po sa akin. Wait lang po ma'am.
Bring.
Ma'am, wait lang po. May emergency lang po for a while. Wait lang po. Sandali lang po.
Sige. Ano kaya ang emergency? Ano ba yung emergency mo? Baka need mong mag-ano dyan. Mag-concentrate. Hanggang ano. Okay. Meron bang pwedeng mag-take over nung ano niya? Nung discussion niya?
Ayan po, sorry po ma'am, may dumating ho kasi. So, ayan. So, yung first half ng ating equation is yung rate ng glucose disappearance due to the effect of glucose itself. So, yung sinabi ko kanina na may ability yung glucose to normalize itself, ito yung part na yun. Then, yung second half is, ito yung, it models the interaction of glucose and insulin in the tissue fluid. So, as the rate increases as either yung glucose or yung insulin in the tissue fluid, yung nag-i-increase. Now, this is the second differential equation. So, it is read as the rate of change in the concentration of insulin in the tissue fluid as a function of time. So, the rate of change in the concentration of the insulin in the tissue fluid is equal into K sub 3 quantity, the concentration of insulin in the blood as a function of time, minus the basal concentration of insulin, then minus K sub 2 times the concentration of insulin in the tissue fluid as a function of time. So, yung first half ng ating equation is the rate change at which insulin diffuses between the blood and tissue fluid. Then, yung next part naman is the rate of insulin disappearance in tissue fluid as it is consumed or broken down. Ngayon na alam na natin yung mga formula na gagamitin natin, kailangan naman natin kunin yung data na gagamitin natin for this simulation. So, we will use the pandas module and we will import the read hand_CSV. Then, using that function, i-read natin yung CSV file which is glucose_insulin, and kukunin natin yung column niya na nagsiserve as time as the index para sa ating table, which is i-receive naman ng ating variable data. Kung makikita nyo dito, which is nasa baba lang nung mismong source code, ayan po yung first 12 na laman ng ating table. Ngayon, since na-read na natin siya, we will call data.head. Then, the head method po is i-read po niya yung first 5 na data sa ating table. So, before natin i-simulate to, meron pa tayong problema na kailangang ayusin. So, kung mapapansin nyo, we only take time with intervals of 2 minutes to 10 minutes. So, hindi natin alam kung ano yung between those parts. So, sabi dito, so in the differential equations, yung insulin in our blood is a function that can be evaluated at any time. So, dito sa data frame natin, nag-record lang tayo in specific times, which is every 2 to 10 minutes. So, para isolve yan, we can use interpolation. So interpolation, ito yung process of determining the unknown values that lie in between the known data points. So dito sa part na to, meron tayong data points around 2 minutes, 4 minutes, 6 minutes, 8 minutes, and so on. And meron din tayo dito is around 16 minutes and 19 minutes. Now, we interpolate the insulin data, and ang ginagawa ng interpolate, so we can use interpolate which takes a series as a parameter, then magre-return siya ng function. So, if we call yung variable I, magre-return siya ng, it will become a function and magre-return siya ng value. So, in-interpolate natin yung buong data insulin data frame, then i-receive yung mga i-return yung value, so pupunta sa I, then if we call I, maglalagay tayo ng number sa gitna, which is number in a parenthesis, which will return a value which is 31.67. So yung 31.67, it is a linear interpolation between the measurements at t equals 16 and t equals 19. So ito yung 16 and 19. So yung 18th minute, through interpolation, nahanap niya na 31.67 yung insulin concentration. Ngayon, ilalagay natin siya sa len range para makagawa tayo ng plot. So, yung first part ng ating table will from the index ng data, gagawin natin t_0. Then, yung last element will be t_n. Then, we will take those two as the parameters for the len range function para i-receive ng t-array. Ngayon, we will use the t-array para i-receive lahat ng values from the interpolated data para mapunta sa I_array. And using t_array and I_array, we will use it as parameters for the make series, and yung i-return yung value mapupunta sa I_series. Now, we can now plot yung mga data na nakuha natin before and after the interpolation. So, ipa-plot natin yung insulin and yung I_series, then decorate it. And ito yung magiging kinalabasan niya. So, yung mga parang solid circles are yung insulin concentration, and yung line naman is yung interpolation natin. So, next reporter.
Hello, naririnig ba?
Yes.
Yes. Thank you. Yan. Glucose and insulin. Next slide. And implementing the model. So before tayo mag-start, let's assume na alam na natin yung parameters ng model. Using the model, we'll implement naman the time series for G and X. Then we can choose the parameters to make our simulation fit the data. So here are the parameters. G0 is equals to 270. K1 is equals to 0.02. K2 is equals to 0.02. K3 is equals to 1.5 E negative 0.5. So, ayan, we have parameters is equals to G0, K1, K2, and K3. So, sa right side naman, we can see a version of make_system that takes params and data as parameters. So, ayan, makikita po natin yung make system def. Next. Wait lang. Nawawala yung ano. Pabalik na ulit. Ayan. So from here, make system takes t_0 and t_n from the data. It uses the measurements at t is equals to 0 as the basal levels. Yung GB, which stands for basal concentration of blood glucose, and LB naman is the concentration of blood insulin. Ayan, ginagamit naman ito yung parameter G0 as initial value and G, then pagsasamahin niya lahat into a system object. Then we use system is equals to make_systems params data. Ayan. Next na. Ayan. Running the simulation. So from here, gagamitin naman natin is yung Asan? Wala. Pabalik pa. Wait.
What happened? Tumigil ba?
Wait lang po ma'am.
Okay. Akala ko baka may problema naman sa akin.
Ayun, sorry po na wala po kasi yung script ko. Ayan, the update function. Ayan, the minimal model is expressed in terms of differential equations. dg over dt is equals to negative k sub 1 times g times t minus g sub b minus x times t gt. Ayan, nabanggit na po yan kanina dun sa formula. So, to simulate this system, we will rewrite them as difference equations. If we multiply both sides by dt, we have dg is equals to negative k sub 1 times g times t minus gb minus x times t, g times t times dt. So, ayan. If we think of dt as a small step in time, these equations tell us how to compute the corresponding changes in g and x. Here is an updated function that computes this system. Next slide. Okay. So from here, gagamitin naman natin is yung def update simulation.
Wait lang po ma'am. Po ng net si Angelo po. Wait lang po ma'am.
Parang kanina walang audio.
Wait lang po ma'am. Nawalan po ng net. So wait lang po.
Okay.
So ayan po. So we updated the function. Then this will be the results. We found that the levels of the wait lang po. So we found out that the levels ng glucose natin is to up to 162. Now, we can now run the simulation. So, katulad po kanina, we updated the function. Kinuha po natin yung sa system. So, as you can see, gumawa rin po tayo ng system natin. Then we take yung laman ng system na yun. Then, yung update function, yung ni-return po ng update function. So, from t_array, in-receive nun yung kinuha ng line range natin. So, kinuha niya yung first index po for the system natin, then yung ending, then yung pinakadulo po nun para po makagawa po siya ng ating x na line po natin. Now, kukunin po natin yung length ng array natin and ilalagay po natin yan sa end. Now, gagawa rin po tayo ng time frame. So, we will take yung nakuha natin from t_array as index, then yung columns po kukunin po natin sa system po from the initialized po natin na mga values. Then from frame, we will use the iLock na method para makuha natin yung values from the initialized part ng system natin. Then magre-return po siya na value na frame. Now, kukunin po natin yung ni-return na value ng run simulation po natin at ilalagay po natin sa results. Then, makikita po dyan na from using the method head sa results po, makikita po natin yung concentration ng glucose and yung insulin sa tissue po natin. So, as you can remember po, kanina po we discussed po, G is for the glucose in our insulin, X is for the amount glucose, then yung X po is for the insulin levels po sa tissue fluid natin, pero yung I naman po is yung blood. So in this case po, X, so ang kukunin po niya is dun sa tissue fluid po natin. Then we can plot it. So from our data na table, kukunin po natin yung glucose column, then ipa-plot po natin yon. Then from the results naman po, kukunin po natin yung G, which is yung glucose po. Then, ipa-plot din po natin. So, i-decorate po natin. Then, ito po yung lalabas. As you can see po, nag-spike po siya from 270, then pababa po siya ng pababa. So, next po is, so the problem sa model na to is, hindi po siya, non-spatial po siya. That is, it does not take into account different concentration in different parts of the body. So, hindi po siya accurate since hindi po niya nakikita yung concentration in different parts of the body. So, the following plot shows the simulated insulin levels in the hypothetical remote compartment. So, in a certain part of interstitial part po ng fluid ng interstitial tissue po natin, pero hindi po siya throughout the body, so a specific part lang po ng body natin. So ayan po yung remote insulin po natin. So ito po yung sinimulate po nila, pero hindi pa rin po siya, so katulad po yung sinabi kanina, hindi rin po accurate since nga po hindi po siya entire body, in specific parts lang po. So now we move on to differential equations.
Para ma-implement yung minimal model sa previous chapter, we rewrote the differential equations as difference equations with a finite time step, which is dt. When dt is very small, the difference equations are the same as the differential equations. From our previous simulations, our dt is 2 minutes, which is not very small. Next, so in effect, the simulations assume that the derivatives dg over dt and dx over dt are constant during each 2-minute time step. Evaluating derivatives at discrete time steps and assuming that they are constant in between is not very accurate all the time. Kaya dito napapasok yung bagong function na gagamitin natin to solve the differential equation using a better algorithm. The new function that we will use is the solve IVP from SciPy, and IVP stands for initial value problem, where we are given the initial conditions and try to predict what will happen. Next. To use it, we have to provide a slope function which is similar to an update function. And in fact, it takes the same parameters, a timestamp, a state object, and a system object. Then makikita nyo dyan sa following lines na makikita nyo under the slope function ay yung pagkuha ng values na gagamitin for our differential equation. And it will return dg dt and dx dt values. So slope function is a little simpler than update function, but because it computes only the derivatives and that is the slopes. Now, we can call the run solve IVP a Modsy library function that makes solve IVP a little easier to use. So dito, ang parameters niya ay system, slope function, and t-eval yung pinapasok dito. So next, tulad ng sa run simulation, it takes a system object and a slope function as parameters, while t-eval is optional because it only specifies where the solution should be evaluated. And it returns two values, and that is the time frame which we assign to results to, and an odd result object which we assign to details. This odd result object contains information about how the solver run, including a success code and a diagnostic message. So makikita nyo dyan yung result ay mapapakita kapag ni-run yung details success and details message, and this is important to check in case anything went wrong. Next. So from results to head, in this example, the rows are time from 0 to 182 minutes, and the columns are the state variables g and x. Because we use t-eval is equal to results that index, the timestamps in results 2 are the same as in results, which is yung result kanina sa run simulation. And dahil dyan, through plotting, it will be easier to compare. So next. So ayan, through the graph, we will be able to compare the two results from the simulation and solve IVP. Yung solve IVP dyan is yung yellow, while yung simulation is yung broken line na blue. Makikita natin sa graph na very visible yung difference nila. Kaya naman through a formula, makikita natin yung relative difference. Next. Ayan, so from diff is equal to results g minus results 2g, mako-compute natin yung percent diff, which is diff divided by results 2g times 100. And based on the results, the mean relative difference is about 0.65%, and the maximum is a little more than 1%. Next. Then itong graph naman na ito ay yung result ng plotting for x, and the difference here are a little bigger, lalo na yung sa unang part ng line. Therefore, if we use run simulation with smaller time steps, the results are more accurate, but they take longer to compute. Next. So for some problems, we can find a value of dt that produces accurate results in a reasonable time. However, if dt is too small, the results can be inaccurate again, so it can be tricky to get it right. So in summary, we implemented the glucose minimal model in two ways: the run simulation and run solve IVP, and compared the results. We found out in this chapter the advantage of run solve IVP, which is it chooses the step size automatically to balance accuracy and efficiency. Also, run simulation is good enough, but in some examples, it is not, so you have to use other function. Next. So, itong exercise 1, papasagutan na lang po namin to. Kahit isa lang po yung sasagot for 10 minutes siguro.
Okay. Ay! Magpa 5:30 na. Ano yun? Ano yan? Magpa 5:30 na.
Siguro wag na lang po ma'am since ito pong exercise ito is similar lang din po sa simulation kanina but
Okay.
different lang po yung DT. So,
Sige.
yun po.
So, meron
So,
pa ba kayong tatapusin sa ano nyo? Na i-report.
So, I think okay naman na po.
So, tapos na kayo?
Apo.
Okay. So, siguro, meron na ba kayong sagot dun sa exercise na yon para pang ending natin? Yun na lang ang i-share
Ayun
nyo.
po. Sige po, wait lang po ma'am.
Oo. Yun na lang i-share nyo pang ending natin.
Wait lang po ma'am.
Sige.
Wait lang po ma'am.
So, ibig sabihin, we will be moving to the next group. So, next meeting will be group 6. Group 6, no? Okay. So,
Ayan po ma'am, kita na po.
oo. Sige, explain niyo
So,
yung
ito
sagot
po yung
niya.
sagot sa exercise 1. So, sabi dito, our solution to essential equations is only approximate because we use a definite step size, which is dt equals 2 minutes. If we make the step size smaller, we expect the solution to be more accurate. Now, irarun natin yung simulation in dt equals 1, tapos i-compare natin yung result. So, ngayon, gagawa tayo ng system 3, equals natin siya sa dt equals 1, then yung makuha natin from the system 3, ilalagay natin sa i-run simulation natin siya together with the update function na discuss namin kanina. Then, i-receive yon ng results 3. Ngayon, i-run na natin. First is yung from results.g, which is yung pinakauna nating ginawa kanina. Then, yung results 3 naman, which is etong nakuha natin from the system and run simulation using sa nireceive natin system 3. Ngayon, na-plot na po siya. May kita po natin na wala rin naman po masyadong difference yung nakuha nilang data. Pero here po, may kita po natin na meron po silang a bit of difference, which is pag makita po natin yung count is 92, yung mean po is 0.53, then yung standard deviation po is 0.29, and so on po. So as you can see po, with a little bit, even though onti lang po yung difference ng ano nila, meron pa rin po a bit of difference when it comes to the results. Yun lang po.
Okay, ayan. So,
Thank you.
yan ay para kay chapter, wait lang, chapter 18, correct? Luis?
Yes po.
Okay. Alright. So, that closes yung ating ano, no? So, again, yung ating ano lang, para ready lang tayo, no? So group 6, ayan, you will cover chapter 19, 20, and 21. Alright. Okay. So, pag-usapan natin yung mga deadlines, no? Kasi ito rin yung diniscuss dun sa kabila, no? So, might as well i-post na natin dito. Did we make a, wala pa. Alright. So, hindi ko pa nilalagay dito. Okay. So, talking about, ayan pala, meron na pala dito, no? Final presentation Friday, same time. Okay. So, okay, hindi ko na siya uulitin, no? So, napag-usapan na pala natin. Right. Okay, so next na gusto kong anuhin is, ngayon kasi ay February 3, ano? And we only have next meeting, which is February 10, to finish yung ating reports, no? February 17, following week is already the finals, no? Which is the parang pinaka final exam nyo, no? Which is final presentation yung project. Right. So, meron lang akong solusyon para matapos natin next week. Kasi next week na yun yung 10, no? Yung mga reports, no? So, we have Group 6, Group 2, and Group 5. Now, para mabilis po tayo at pwede nating pagsabay-sabayin, gawin na po natin yung ating mga presentation and let's put it on video. Ayan. So, yung video na yan po yung ipi-play natin para mabilis po tayo. At pwede nating paghati-hatiin yung oras dun sa last meeting divided sa inyong tatlo. No? Para hindi tayo talo. No? Para lahat nakapag-present at yung group na yan dun sa inyong naka-assign sa inyo may natin, no? Mapakita natin. So, Group 6, Group 2, and Group 5, no? Mag-prepare po tayo ng ating presentation. Ilagay po natin into a video, no? Tapos, i-play natin. Hopefully, tayo ay ano ba ang magandang naka-assign na time, no? So, tayo ay, sandali lang lagay natin sa time. So, we normally starts at 3. So, we have 4, 5, and 6, no? So, actually, 5:30, no? So, kung hahatiin natin yung oras na yan, pwede po tayong tag po 45 minutes. So, 45, 45, 45, no? Kasi, para no? Para yung may matitira hanggang 5:30, tapos tayo, no? So, i-time po natin yung ating presentation ng video ay umabot po ng 45 minutes. Ayan. Hindi na po tayo magpapa-exercise, no? Para dire-diretso. Para matapos natin yung tatlong grupo. Okay? Wait. I-confirm ko lang baka yung audio ko ay hindi maliwanag. Maliwanag po ba yung naririnig nyo po ba yung sinabi ko? Ayan. Pwede po paki-confirm. Baka ako'y nagsasalita wala akong audio. Ayan. Okay.
Yes po, ma'am.
Ayan. Okay. Good. So, ulitin ko lang yung ating last meeting na para sa ating reporting is next week, which is February 10. Para naman hindi tayo talo, no? I-ready na natin, no? I-make sure i-time natin na 45 minutes yung kada presentation natin. Ilagay na natin sa video para dire-diretso, no? Ayan. So, yun yung paghahati-hatian nating oras para dun sa next meeting para lahat tapos yung tatlong grupo. Kasi tapos na yung last, no? Okay. So, yun ang ating resolution doon, no? Para ma-cover natin yan. And then, the following week, ayan, February 17 yung ating final presentation. Okay, yung sa ating final presentation, we follow the same format dun sa presentation natin. And, we use, of course, the same rubric. Now, nasa inyo na lang ang desisyon kung i-improve nyo ba yung ginawa nyo last time or gagawa kayo ng bago. I would suggest, para hindi kumain ng oras, ay i-improve nyo na lang yung i-present ninyo, no? Para hindi na kayo mahirapan. Kasi, sayang din yung time, no? Ayan. So, again, we'll use the same format to sa presentation. And, yun na lang, no? So, para maidagdag yung inyong improvement to sa inyong ipe-present. Okay. Right. So, ano pa ba? So, ayan. 5:30 na po tayo. So, maliwanag po ba yung instruction dun sa mga magre-report next meeting? Paki-confirm naman po nung bawat grupo. Yan ay sige, para maliwanag, ilagay natin. So, group 6, yung leader or anybody, okay, paki-confirm. Yung ako na pick up yung instruction, mag-ano lang po tayo ng reaction. Ayan, react lang po tayo, group 6. Group 6. Anybody from group 6? Wala nagre-react. Sino ba itong members ng group 6? Teka, tingnan natin. Saan ba si Francis? Francis! Sino ba yung grupo ng 6? Group 6. Kailangan ko ng confirmation eh.
Wait po, ma'am. Check ko lang.
Si Maverick. Okay. Nag-react na raw sila. Sorry naman. Okay, next. Yung group 2. Okay, paki-confirm yung instruction. Gagawa ng video yung presentation. Mag-react na po. Mag-ano lang po tayo ng react. Either okay or taas kamay. Ayan. Naabangan ko sa listahan eh. Group 6. Okay, good. Sina Diana. Hindi. Group 2 pala, sorry. Okay na yung group 6. Group 2 pala, sorry. Group 2. Group 2. Ayan, okay. And then, yung last na grupo, group 5. Okay, group 5. Taas kamay. Okay. Okay na tayo. Maliwanag na. Alright. So, tayo po ay umabot na sa ending ng ating klase. Kayo po ba'y meron pang clarification dun sa ating gagawing mga activities this coming? Or meron ba kayong clarification dun sa diniscuss po ng last na group? Okay, any clarification? Right? Okay, kung wala na po kayong gustong i-clarify, pwede nyo naman akong i-message, no? At maliwanag na yung instruction natin next meeting. Ayan. So, pwede na po tayong mag-move on sa ating next na class, ha? Okay, salamat po for coming today. Ayan. Friday. Happy weekend, no? It's a weekend. Kung wala kayong klase bukas, ayan, it's a happy weekend. Okay? Thank you for coming today. Ayan. So, nag-end tayo ng 32 ang ating attendance. Ang topic ay, ayan, yung ating pang-ending na topic ay group 3, chapter 18. Ano nga yung chapter 18, group 3? Anong title nun?
Glucose and insulin po.
Glucose and insulin, yung minodel natin doon, no? So, application kasi yan, kaya meron tayong world map. Ngayon, next naman, glucose insulin yung ating minomodel yung data, no? Okay, yun po yung ating sa topic. Ayan, sa topic. Okay, chapter 18, glucose and insulin. Ayan, nasagot ko na yung tanong ni Pabalan, ni Mark Jeremiah. Yan din ang isasagot nyo sa inyong attendance. Okay? Alright. O sige, okay na tayo. Nag-ending na tayo sa 32. Ayan, attendance. Okay, thank you. Thank you for coming. Sige na po. Ako ililipat na sa next na class. Thank you.
Thank you po.
Ayan. Thank you. Okay. Right. I-end ko na ang video natin.